Hello, good morning. My name is José Luis Fernández Villacañas Martín, or you can call me Pepe for short. I'm not at the beach, I wish I were, but I'm trying to keep my holiday memories as close as possible for the time being. Today, we have the pleasure of a very distinguished speaker in the field of city, specialized partly in smart cities and traffic management, Professor Dirk Helbing. He, together with another 9 distinguished experts in the field of complexity science and smart cities, have produced a position paper that will soon be available in the preprint site and hopefully soon after in Nature, on why complexity science is useful for the management of smart cities. Okay, this may be interesting for some of you that are at the stage where your digital twins of your cities start getting complex or complicated enough so that you can do simulations of scenarios on what would happen if I do this, what would happen if I do this other thing. I mean, and the argument of today, what Dirk will try to explain, that for the models that you should use, you have to take complexity science into account. That's the main argument. I must remind you that the meeting is going to be recorded. So if you have any objections, please let us know immediately. Otherwise, it's my pleasure to give the floor to Dirk, who would speak for 40 minutes. And then he will have 15, 20 minutes of questions. He'd rather have the questions after he speaks, unless there is something very pressing. And then you can start putting your questions in the chat, okay? So over to you, Dirk. Thank you.
Thank you very much, Pepe. It's a great pleasure to be with you. Is the recording started? So I've chosen the provocative title, Should We Build the Matrix? Some Challenges of the Digital Twin Concept. And I will start with the take-home messages, okay? So we can focus on that. The world is made up of coupled complex dynamical systems. Everyone knows that, but it's important because these systems often behave in a counterintuitive way, and the purely data-driven approach doesn't work. Complexity science, however, can help understand the behavior of such systems better. It can help manage these systems better, and complexity should not be seen as our enemy. It can actually be the solution. Digital twin technology must take the complex network nature of our world into account. It must be designed to support interactions in space and in networks, self-organization, and co-evolution. Now, these are exciting times. Digital revolution is ongoing. We're living in a big data world. And some people saw that this would mean the end of theory. If we just had enough data, then basically the data would tell us the truth. We would see what is wrong, and we would see where the system is broken and what we would have to do. And the idea was that we could now build something like a crystal ball to predict the future. And in fact, the military is working on this. And similar technology is now basically entering a civil domain. And the question that we need to ask is, was Chris Anderson right? Or do we need to be more sophisticated? And of course, you can expect that Chris Anderson was actually too optimistic, right? So how difficult is it to create digital twins? Well, if you just want to represent the infrastructure, like building and streets and all this, it's actually pretty doable. You know, you take satellite imagery and all sorts of other photographs and sensor measurements, and as long as the environment doesn't change much, you can get pretty good representation, right? But already when it comes to land use models, things get actually more tricky. because then you have an interaction of different effects. People choose routes from origins to destinations. And here also the demography of the population plays in, the economy plays in, people go to work and back, and all this basically creates a complex dynamics, all right? Wages and revenues, house prices, and so on is all interconnected. And I'll show you a few slides of the team of Michael Betty, CASA Institute in UK. And basically those slides stress that the first requirement for these models is that they interface with several others. And that means there will be complex interactions between all sorts of things. The second requirement is that they are visually accessible for stakeholders. And the third requirement is that we can set up scenarios within the visual template. And of course, there are many other requirements. And as you can see over here, the mapping of the environment gets pretty detailed. There are different layers of information, and it takes, of course, some time to collect all the data and put it all together into one model. And then you have to not only take care of the sequence of model functions, but and the map graphics, but also you have to determine parameter values, which requires calibration and validation, sometimes pretty tricky, actually, not trivial at all. And then eventually you have a representation of the system, and you could look into what if scenarios. For example, what will happen if we put a new airport into a certain area around the city. And then you've planned for all of this, you know, and suddenly the virus comes around the corner, and all the planning was in vain because the situation has changed entirely. So we need to learn about post-pandemic cities, how to plan for them, how to be flexible, adaptive, resilient, sustainable. And this is quite a challenge, of course, and it cannot be done without complexity science. Here are some books, by the way. And of course, Europe is now also very much engaged into creating digital twins, and just mentioning the Destin or Destin-E project, which is trying to understand the climate change, but also the impact of people on climate and the other way around. And the question is, how difficult will that be? Well, it already starts with the weather, which is turbulent in the very sense, in the sense of turbulence, which is a physics concept actually, and it means a system in which small changes, in fact, the smallest changes you can imagine, could have over time a huge impact and make a big difference. And that means those systems over sufficiently long times, typically weeks, maybe days even, would not be predictable. Now, climate is of course not the same as weather, and you can basically try to average over weather and then basically get climate. But also that is more tricky than expected. There's more than the need to represent climate change in a three-dimensional grid. There are also network effects. They can be over very large distances. And for example, El Nino is such a well-known example where some apparently little changes can have really big effects in many areas of the world. Now, in complex dynamical systems, you need to know there are basically two kinds of situations, stable ones and unstable ones. When we have a stable situation, we would typically have what we call an attractor. That means a certain kind of dynamics which is self-stabilizing. And then basically things are well predictable, well controllable. And we don't need to be so much worried about it because the system would tend to go into its natural state described by the attractor. But when the system are unstable, you know, like when there's bad weather, basically, then what happens is things are pretty unpredictable. And the slightest changes can really, over time, make a big difference. And another systems that shows this kind of behavior, which is well known, is chaos, even deterministic chaos. That means there's basically a mechanistic principle behind the dynamics that we can write up, but still we cannot predict over long times the behavior of the system, because even the 10th digit after the comma in the initial conditions could make a difference over time. Okay, so sensitivity altogether is an issue in many of these systems, not only in COVID prediction, where we've seen that they've often been wrong. This is because even if we would know the exact equations that describe the dynamics, there would still be confidence intervals of the parameters that we can determine. And within these confidence intervals, it could be any parameter. And that means there could be different outcomes and sometimes pretty different outcomes. And so even for the world populations, it's difficult to say what level will reach in the future. Also for peak oil, predictions have consistently been wrong over time. And it's also difficult to predict the exact climate change or global warming effect, okay? And that, of course, is concerning. We'd like to be better in that. And there are many problems of this kind. In fact, one could say the big unsolved problems result from systemic instabilities. And this includes crowd disasters. It includes unstable supply chains, booms and recessions, financial, economic, and spending crises, tragedies of the commons, such as overfishing. Climate change is also one of them. Unstable social dynamics and spreading of crime, terrorism, conflict, revolutions, mass migration, residential segregation. And even though these are difficult challenges, all of them have in common that there's a complex dynamics behind it, and still it's possible to model this dynamics to some extent, to understand fundamental features of this dynamics, and also how this dynamics can be changed slightly to create better outcomes, because the outcome of the complex dynamical system is often determined by self-organization, and changing the interactions within the system would change the outcome. That outcome could be positive or negative depending on the interaction. So basically what we need to learn is what are the interactions that we need to have the desirable outcome as a result of self-organization. So here's just one example of the models that have been created for those kinds of problems. There are models for all these problems. Just need to look up the literature. And in fact, there's good progress in the field of complexity science and computational social science. This model for residential segregation has, for example, been developed by Thomas Schelling, a Nobel Prize winner in economics. Okay. Now, given that fact that it's often difficult, if not impossible, to make long-term predictions, we should, in many cases, focus more on prospective modeling. That means scenario analysis to get an idea of the possible different alternative developments of those systems and how we could actually choose one of them a favorable scenario, in fact. Now, even though there are limits to control, as we can see over here, we're basically, even in the simple exercise of driving in a circle, an undesirable outcome happens that nobody wants, which is a traffic jam. And even though, as a result of that, society cannot be steered like a car, we can still learn how to get control of those kind of systems. So what I'm showing you over here is a simulation of stop and go traffic as we all know it. And later on, we'll try to see the reason for that undesirable phenomenon. So in a few seconds, we'll just get so annoyed that we are leaving the car, we'll take a helicopter, and that will allow us to see the reason for the stop and go traffic. There's an on-ramp actually where some vehicles are trying to enter the freeway. That produces some small disruptions of the freeway traffic flow, and those are amplified, which causes the stop and go traffic we've seen before. Now, what we'll do is we'll equip some vehicles with driver assistance systems. They will be able to use, say, a radar sensor to measure distances and relative velocities and have the car accelerate and decelerate automatically, or autonomously, as if you want. As you can see over here, the traffic jam has disappeared, even though there was not a traffic control center controlling every single car. The only thing we have done here is we have introduced a feedback effect based on those real-time measurements by a certain fraction of cars, and 40%. So this is really interesting because we don't even need to equip all the vehicles with that kind of technology. Just changing the behavior of some of those vehicles will dissolve traffic jam. And what we're doing is basically using the Internet of Things, which can now basically allow us to make self-organization work 300 years after Adam Smith's idea or concept of the invisible hand, okay? But that requires, okay, do you still hear me? That requires actually minimally invasive interference with the system. It's typically not a good idea to really try to get control of every single element of that system. Another example is actually the bunching of buses, right? So they should come, say, every 10 minutes, but you'll wait sometimes for 20 minutes, and then one of the buses is overcrowded and the next one just comes 1 minute later. Now, even though those buses have detailed schedules, this often happens in many cities around the world. And in fact, knowing about self-organization, the solution would be to change again the interaction mechanism between those buses and not to force them to stay in the schedule, which obviously they don't manage because passengers arrive in bunches, okay? Now I'll show you some more examples of how we can actually improve transport. But first, before I do that, I'll have to introduce another complication in complex systems, which are network effects, okay? The entire world now is networked, every single systems almost, and those networks are also interconnected with each other. This has important implications because we'll not only have the intended effects, but also side effects, feedback effects, and cascading effects. And that can be really, it's pretty serious. It can introduce uncertainty and uncontrollability in the system. Here is just one example. Yes, and this example shows you basically that a very small perturbation can mess up the entire system. And we've seen that actually in our world financial system, where the bankruptcy of Lehman Brothers has actually triggered the bankruptcy of hundreds of banks and basically crashed the financial system for some time. In fact, the problem is still partially unresolved. It's even growing bigger over time. We see similar problems in power grids at times where there have been blackouts that have been spread out all over Europe. And also here, there can be pretty unexpected complex dynamics where, say, a blackout in Spain could actually trigger a huge problem out there in Middle and Eastern Europe, as we'll see in a few seconds. And so in many of these complex systems, the effects are pretty counterintuitive and unexpected. And we're seeing a similar problem also in the case of the current pandemic, of course, which is also based on a cascading effect. Nevertheless, it has been possible to understand the spread of diseases by combining different kinds of data sets. One has to consider passenger volumes between airports of different countries. That allows one to define a new effective distance. And within this effective distance representation, suddenly there is a circular spreading phenomenon that allows us to anticipate actually the disease spreading to some extent and take preparatory measures in principle, okay? Now, as networks interact with each other, things get even more complicated. So a blackout in the electrical system would cause blackouts in, say, the water system and the gasoline supply in the communication system and so on. And we've spent some time actually mapping out those causality networks of what happens when a disaster strikes. In fact, there could be often secondary and tertiary disasters. For example, earthquake could cause volcano outbreaks and tsunamis. So things would often get much worse than expected, but still we can understand this dynamics and prepare for that in advance. Now, even though we have those cascading effects in networks, we can still actually master the dynamics. And actually, what we have created is a self-organized traffic light control, which was somehow inspired by the self-organization that you see in that intersection over here. Quite surprising. So if you design for self-organization, then you can actually have pretty efficient and desirable outcomes. So what we wanted to do is to create a new kind of traffic light control that is made for complex street networks that can handle traffic disruptions and particular events such as Olympic Games, pop concerts, and so on. And we have been inspired here by another self-organization phenomenon observed among pedestrians, which is oscillatory flow at bottlenecks. So we have come up with a pressure principle that allows the flows at intersections to create self-organized oscillatory flows that can be used to define traffic lights. Okay, so basically here the traffic flow controls the traffic lights rather than the other way around. And why is that a good thing? Because as you can see on the right, there would be self-organized green waves, which would be very efficient. In fact, this principle has been shown to allow us to save waiting and travel times, which also is good for the environment because there would be less gas consumption, less CO2 production. And this principle has been implemented in 2 cities, so far. Further cities are about to come. Dresden, for example, and Lucerne, they call it the super traffic light because it managed, it's unbelievable, but it really managed to shorten the waiting times for all the traffic participants. So more green for everyone. Now you would maybe ask, what about machine learning, artificial intelligence? Isn't that going to come up with even better controls? And the answer is no. What we have created over here is actually more efficient energetically, saves learning times as compared to machine learning and AI of today. It's based only on interactions between neighboring intersections. Of course, it's based on sensor measurements in real time and short-term predictions, but it doesn't necessarily need a centralized control center. That is really very interesting. So we're using here the physics of traffic flow and the dynamics of complex systems to let the system self-organize towards a coordinated state of traffic flow that would spread throughout the entire city. So this is absolutely innovative. There's even a patent, by the way. But anyway, so how could we extend that principle and use it to solve the world's problems? So for example, to make the world sustainable, we all know if we had a circular economy, that would really change the situation quite dramatically, but we didn't get there. And so how do we manage to get away from a wasteful system where we produce maybe 50 tons of waste in a lifetime? How would we get away from the supply chains of today that are so wasteful towards a circular economy? And our approach is not to go the route of regulation or, as businesses often say, over-regulation, but we suggest to use the Internet of Things. We basically measure jointly the impact that our decisions and behavior on the decisions of businesses and their action would have on the environment and on others. So we can now measure noise and CO2 and temperature and all sorts of poisons and waste of all kinds, like, you know, glass and plastic and steel, and all these kind of things could be measured now with the Internet of Things very easily. And now what we need to do basically is we need to increase the positive externalities, reduce the negative ones, and ensure fair compensation. But we would need to have multiple feedback loops, right? That requires multiple incentive systems. That means not just one kind of money in order to try to control the complex world of today, but we would need to have multiple incentive systems, multiple currencies. And that can now be created by combining the Internet of Things with, for example, blockchain technology. We have worked on such a system, which we call Finance 4.0, a socio-ecological finance system, which would actually introduce new forces into our economy in order to promote a co-evolution of that system towards more sustainability and towards a circular and sharing economy. And that is something which I think would really change the situation dramatically, using a paradigm change in the thinking about the problems of the world, a paradigm change from focusing on the components towards focusing on the interactions between the components, which determine the complex dynamics. So I'm now moving on to the summary and conclusions. Creating digital twins is not a trivial task when it comes to highly dynamic systems involving humans in particular. So should we build the matrix? Well, first of all, I'm not sure it would succeed. Second of all, would it be desirable? So we already have difficulties today to refine raw data, to turn it into information, and then knowledge, and then wisdom. It's a pretty tricky process which cannot be fully automated. According to scientific knowledge of today, digital twins would never be identical. And that's not just a matter of sometimes slow convergence of machine learning that would run on all the data that we feed into those systems. There are also those issues that you've heard of, correlation versus causation. In many cases, it is not so clear. Is there a causal relationship? And if yes, which way is that causal relationship, you know? So it's a big difference if crime causes unemployment or unemployment causes crime, for example, right? So if crime causes unemployment, then pre-crime would be a possible solution. If it's the other way around, most likely, you would need to have social policy to solve the problem, right? Further on, there's a problem of false positives, and that cannot be eliminated by more measurements. The problem will stay around when it comes to catching terrorists. Actually, there are a huge number of false positives, so you need to have all sorts of filtering mechanisms. In the end, you often have a lot of people filtering the alarms that those systems give. And it could even happen that if you don't correct for false positive effects, you could end up in economic lockdowns that maybe would be avoidable. So, you know, if you just take a data-driven approach, that could be sometimes very misleading. Then also there's this phenomenon of overfitting, you know. So if you have too much data, you could easily fit to noise, or you could basically start detecting patterns in data that actually are meaningless. And that is also a problem because you would come to wrong conclusions, you take the wrong policy measures, and so on. So sometimes, and that's why scientific knowledge is needed, simpler models have more predictive power. They're not as good in describing a data set, but if you want to learn something for another city, for example, you need not descriptive, but predictive models. And there sometimes simpler models are better for the very same reason that overfitting can often occur if you use too many parameters in your model, okay? And then there's a surprise that in some cases, noisy data can be better. So this is an example over here where we have actually tried to describe the outcome of opinion formation or social behavior in a system. And it turns out that even though we can reproduce with that model 96% of individual decisions, which is an enormous accuracy for social behavior, the macroscopic behavior of the model is not, of the system is not correctly described. But if we add some noise, actually the macroscopic outcome that we're of course interested in from the perspective of policymakers would be better reproduced. Also, take into account that the data volume grows faster than the processing power, and as the networking in the system goes on, systemic complexity grows even faster than the data volume. So surprisingly, even though we have better technology and more data than ever, there's a tendency to lose top-down control, and we require a different control paradigm, which is distributed control and self-organization. And this slide also makes clear why centralized control has limits in the world of today, where we have actually heterogeneity, where we have fluctuations, where we have large variability, dynamics, noise, and so on. So all of this actually has implications for the control approach that we need to take. And that again speaks in favor of distributed control and self-organization. So if you just understand those systems, then we can let the system work for us, and that self-organization create the outcome that we'd like to have. Also, finally, consider that people are really more than physics, right? So a purely data-driven society would miss out important things such as human dignity, empathy, love, freedom, consciousness, intuition, spirituality, culture, and so on. So actually, quite a lot of tech billionaires have warned of creating the digital matrix, and actually think we need to learn to break out of this. Of course, we should use digital technology for our society, but how to use it well is tricky, and that's why you should read a few books, and that's why you should collaborate with the complexity scientists in Europe, in the world. Europe is actually pretty well positioned over there. We have some very good complexity scientists, and if you build digital twins, complexity science need to be taken on board, right? So again, the take-home message is the world is made up of coupled complex dynamical systems. These systems often behave in a counterintuitive way, and a purely data-driven approach will therefore often not work. But complexity science can help you understand the behavior of such systems, can help you manage these systems. Complexity is not our enemy. It can actually help to find good solutions. I've demonstrated that, for example, for the self-organized traffic light control. Digital twin technology must take the complex network nature of our world into account, and it must be designed to support interactions in space and in networks and self-organization and co-evolution. So with this, I'm ready for your questions. Thank you for your attention.